Good evening. Welcome to another episode of the AI for Good Capstone event, live from Harvard Square. My name is Bruce Wang. I am the director of the master degree programs in information technology. Tonight, what we're going to do is to share with you some of the experience from our alum, our students who went through the process of admitting into the master degree program and then graduate. So our first guest speaker we want to have a conversation with is one of our proud alum who graduated in May last year with the degree in data science. Brendon Gory. Brendon, good to see you. Welcome back on campus.
Thank you so much for inviting me to talk about this wonderful journey. Appreciate it.
Excellent. Now, Brendon, when he was a student here, the last step of his degree program is what we call a capstone project. And he worked on a project sponsored by NOAA. What is NOAA?
NOAA is the National Oceanic and Atmospheric Administration.
That's NOAA.
Yes, government agency that's responsible for detecting, monitoring sea surface temperatures, fisheries, wildlife, a lot of weather events, and they have many buoys and satellites that register and read data throughout the world.
Wonderful, right? So while he was a student, he worked on that project sponsored by NOAA. And when he graduated, and they like him so much, and they actually hire him, and he's now a full-time researcher at NOAA. So what we want to do is talk to Brendon and see if we can get him to share some of his experience as a student in this program, and as well as his experience working as a researcher at NOAA. So when did you start it here?
I started September of 2021. I was in IT for about 20 years and just felt as though I needed a change. And when I went for my master's, I ultimately wanted to work for an NGO or AI for Good. So it's very fitting. This is where I ended up. And I just remembered that going through the process that this is exactly what I wanted to do. And it was just divine providence that NOAA was one of the sponsors for my capstone in spring of 24.
Yeah, I remember really well that the process in the capstone experience, right? We call it the capstone experience, is that students come on campus and that they form teams and then they select projects. And when Brendon selected the project sponsored by NOAA, and I mean, he told me that, remember, this is exactly what he told me. He said, I want to work at NOAA. This is the job I want, right? I mean, that's what you said. And so he actually got it, right? And so tell us a little bit about the project that was sponsored by NOAA.
Well, our project was sponsored by the chief scientist, Dr. Ludo Brucker, and my teammates are the people who worked on the project with me, Rushi Atana, Juliana Bacon, Matthew Thanos, and Sulu Thomas. We worked on predicting sea ice motion and the expanse of sea ice. We looked at a specific area in the Arctic, the Beaufort Sea, just because there was so much data and limited amount of time. We thought from January to May, we would have tons of time to do tremendous amount of research. But it really came down to like 3 or 4 models that we were able to work with and do some predictions that really added to some of the knowledge base that NOAA is looking for. And that's where Dr. Brucker, during the term, when we started, I said, this is exactly where I want to work. And he remembered that and said he had a position for me. And that's what we are continuing to do. He's interested in using AI and machine learning and to continuing the research and development on sea ice, the expanse of it, and more prediction and AI based modeling around that data. So we are continuing the initiative that was started at our Capstone.
So the project is all about ice,
Sea ice, yes.
right? Sea ice, yes, yeah. Why? I mean, what's the significance? What's the importance of studying sea ice?
Well, you could probably ask that question for the NASA groups that will follow all our talk. Learning and understanding our environment is just so tantamount to understanding the climate that we're in now. And sea ice does have a bearing on weather, especially in the mid latitudes. And if there's less sea ice, weather in the mid latitudes can become more extreme, as we've seen in the past 10, 20, 30 years. Most importantly, the scientists aren't sure, but 2030, 2040, 2050, there could be an ice-free summer in the Arctic. And that certainly would have implications for new shipping routes, but also deleterious effects on the wildlife that is up there. So there are impacts for us, for our civilization, for nature, for wildlife on studying sea ice and what happens up there, because the Arctic is so remote and there's so few sensors and measurements that are going on up there that any type of insight we can gain with this part of the world would just have a tremendous impact.
It's fascinating. Right. So basically, what do we do? We use AI, machine learning, computer visions, right? And for this study. So what's the most challenging situation?
Well, I think that the most challenging is that we want to take big bites at this, and we want to look at all the sea ice across many decades and years and temporal periods, and try to figure out what's going on. And even though AI is amazing and it's growing so fast, there are limitations with how much you can process at a certain time. And we're really interested in just the next few days of prediction of sea ice, because that could really make a difference. So I would love to be able to have AI to predict what is going to be the sea ice in the next 6 months, 6 years, 60 years. But there are limitations with the amount of data that we have. And as I mentioned before, in that particular region, the Arctic region, the tools that we use to measure in situ buoys, some of the satellites that we used, they still are kind of sparse. So there are a lot of blind spots in that area. So we talk about with data, we don't want to necessarily impute the data. We don't want to make up data. So we have to rely on machine learning and AI to kind of fill those gaps, fill the blanks of what's going on in that region. So that's certainly a big challenge, but we're up for it.
2021, that's when you started the program, right?
Correct.
Okay. And so how long it take you to get to the capstone?
So there's just about 2.5 years.
2.5 years.
Yeah.
Okay. All right. So in this 2.5 years, what is the most memorable experience in the program?
I would say just my classmates. I mean, the professors have all been amazing, very helpful. The information that they give us is very timely and very current. But the classmates that I've met along the way and learning their journey and where they are in the journey and what they want to do. Admittedly, I was one of the more senior of my classmates. So some of them were just starting the profession or increasing their skills in a current position, where I was really going for a career change. But just seeing diverse background And not everybody was coming in with a math or computer science degree, coming into data science, and meeting everybody and the suite of skills that they had and how they contributed to the department, I think was just a long lasting memory that I'll have.
Wonderful, wonderful. So now you're at NOAA.
That's correct.
So what do you do?
Well, my day pretty much starts like one of the projects that we had at class, one of the homework assignments, that we're giving a set of data, and we need to figure out what's the story behind the data. So we constantly are fed information from buoys, from satellites. The the larger goal of NOAA is to disseminate information. Give that to academia, give it to researchers, give it to other scientists throughout the world, and be kind of a consortium for all that data where people can access it. So our job as data analysts, data scientists, data engineers, it's kind of the husbandry of that data. Make sure it's available, make sure it's up, make sure it's reliable. And so that's what our current day looks like, just an inundation of data. And there's a lot of exploratory data analysis that we're doing. I currently was just working on buoys in the Arctic region, and we are going to start forecasting using machine learning and AI. We're going to start forecasting the movement of those buoys, which we can translate into sea ice. And there are other scientists and other departments that are going to be tying this all in together to get more of a holistic cryosphere type of idea of not just the Arctic regions, but all weather patterns and how they are all interrelated. So that's NOAA's responsibility, is really making that data available and making it accessible so other researchers can contribute.
Wow. Okay. Because I know that NASA uses NOAA's data. Right.
I'm sure. I'm sure NOAA uses NASA. Well, we use some. There are some interplay with satellites that are up there, and we share the data. But yes, I think it's a very good relationship between the two agencies.
Right. And will you say that the skills, the knowledge you gain from the program, it has a direct application, relevancy, right, to what you do?
I could not do anything at my current job if I didn't have the education at Harvard. There's nothing I knew programming, but that's it. Any of the statistical analysis, any of the tools, the latest cutting edge machine learning like UNets, neural networks, computer vision, that was all learned and applied in real time. So anybody that takes the classes here, you will use those skills in whatever profession you want to go forward. So yes, absolutely. I mean, it was very, very crucial and critical. The things that I've learned, there's no way I'd be able to do my profession without that.
Now, like I said earlier, that I remember you told me that, hey, this is the dream job. This is what I want to do, right? And I mean, while you were a student here and working on your capstone project.
Yeah, yeah.
So now that you worked there for a while, did it turn out to be what you expected?
No, it was better than I expected. The teams that I work with, the quest for knowledge and for truth and data accuracy, and just feeling as though I'm contributing and hopefully leaving the world a better place after I leave and my profession. It's more than I could ever have hoped for.
Excellent, excellent. Well, thank you very much for coming back on campus and sharing your experience with us. And what we're going to do tonight is that we're going to share more experience from the other cohort, right?
Thank you so much for inviting me, and I'm looking forward to the other presentations.
Hope that was a good information exchange, that the conversation with Brendon. After Brendon, we have another cohort, right? And who came on campus and that to finish up their master degree in the field of data science. That we're fortunate that have our sponsors and that NASA that sponsoring our cohort, our class again, right? And now NASA has been a great partner and has been helping us and has been sponsoring our data science capstone projects. So we have a long and great relationship there, and so we're fortunate tonight that we have two NASA teams, two capstone teams and sponsored by NASA from the previous semester. And they have done that. They have completed their capstone project and provide extremely wonderful insight on the problem that they were looking into. So what we want to do now is that we want to talk to these two NASA teams. Now, these two NASA teams each team has 5 members. And so tonight we have 2 members from each team in the studio. And we have 3 members from each team is actually online, joining us via the Zoom session, right? And so we have 2 NASA teams, and Monica and Cassie is basically one of the team, right? And Ian and Christina is on the other team, right? And so I don't know if you want to quickly introduce your team.
Team 1, as we were called for the past few months. We'll do our formal presentation later, but yeah, that's us. We have actually 4 members, not 5, but we were short one.
Okay. All right.
And we've got the other team there.
Yeah, I'm Ian. This is Christina, and we did the cloud to cloud project, which was using computer vision to map the tops of clouds and create point clouds out of the clouds and process them on the cloud. So it's been a lot of clouds.
Right. Now, I believe that we actually have 3 of our scientists and sponsors that joining us, and that I don't know whether they have joined on online remote, and that is. So we have Dr. Lang, right? And we have Dr. Peterson, and we have Dr. Quick. And so I guess we'll let our team here to see if they can find them in the online sessions, and if they do, and bring them to the screen, and then we will see if we can ask them to say a few words, right? And so I see Dr. Lang has popped up here. Hi, Dr. Lang.
Hello, how are you?
Very good, very good. All right. And so thank you so much for joining us, and thank you very much for helping us and supporting our students and working with us on the Capstone project. So if you'd like to say a few words.
Yeah, well, I appreciate the work that they did. They helped us attack a couple of different problems that we've been puzzling on how to move forward, and they offered their services. One of them is to kind of look at, well, they'll tell the details, but one of them is to kind of look at how we might be able to recreate certain types of passive microwave data in future where we maybe don't have those instruments with all the frequencies that we might like in the future. And the other helped us a lot with a special airborne instrument that we maps lightning from above the cloud.
Thank you so much. I mean, that's wonderful. And I also see Dr. Peterson join us. And hi, Dr. Peterson. Thank you for joining us, and also thank you for supporting our students. And you'd like to say a few words?
Yeah, hello. So I'm Dr. Peterson. I'm at Georgia Tech. I was working on this project with Dr. Lang as well as with the Harvard team. It's a really interesting idea to use this machine learning methods to try and predict if we have a missing passive microwave channel which might be the case on future satellites as we go to more, smaller and more efficient designs, kind of getting more to the CubeSat realm. Some of the more cumbersome and, difficult to operate antennas might not be feasible in the future. And so if we can kind of bridge the gap between all the work that's been done over the past 30 or more years with all these retrievals and all these climatological measurements, going forward with this kind of new paradigm of smaller, more lighter weight type instruments, is really helpful. And the Harvard team has been fantastic to work with and produced far better results we were getting previously.
Thank you. Thank you very much. And now I believe that I think that Dr. Mason Quick said that he was going to join us, but when he comes in, and we will introduce him. Well, let's have a conversation with our team here. And so now y'all came in on campus in summer 2024,
Yes.
right? Summer
That's right.
2024.
That's right.
And the summer 2024 is what we call the pre-capstone residency. It's like 3 weeks, right? And tell us your experience in that 3 weeks, right? And and now the goal of that 3 weeks residency is that we basically form teams and we select projects, and then they're going to start. They work on the proposal, what they're going to implement during the next semester in the capstone. And so they work with their sponsors and identify the problem and then put the proposal together, right? But besides that, and they also have a lot of on-campus activities, a lot of enrichment activities and team building activities. And so maybe that you can share some with us, right? And so I see the picture right in front of us. And what is the picture?
This is actually from your generosity to take us all out for cheap noodles the first night of the program, of the summer program. And it was a chance for everyone to bond and come together. And I have to say, the summer program, the summer experience was really tied the whole master's program together, because we spent however many years on Zoom. All of our classes were online, and the teachers, the students, they were just little pictures, put in double speed sometimes, the lectures. So it was nice to see the faces of these people that I had been responding to in discussion posts, be like, oh, I actually commented on your post a few months ago. So this was a chance for us to all bond and meet each other, and I think we had a good time.
Yeah. So now you got some other pictures here for us, right?
Yes, we do,
And
actually.
okay. So what is that? I saw Christina.
That's
I saw
Christina.
Cassie, right? So what were you doing?
For the first week, there were rec center activities, and a lot of other extension students also signed up for these activities. So it's not just meeting folks from data science program, which I was very excited to finally meet a lot of my classmates and people I worked on projects with in person. But I also got to meet people from other parts of the extension school. On the top row, I signed up for like sailing. I also met some other Harvard grad students, and then we're invited to do a barbecue and watch the 4th of July fireworks. And then I guess the bottom row, I think Guilherme took some of these photos, but on the bottom,
That's our classroom.
Yeah, that's our
spent the whole
classroom.
summer in that room.
Yeah, you can see Ian in there, and then just we're all
It's proof that we did study. We did do some research. So in that room.
And then there's Annenberg Dining Hall on the bottom right.
I can show you some others.
So one of the things that we had an option to is to sign up for housing, to be able to come in and stay for the whole summer term. So I was able to sign up for housing in Claverley Hall. I think Christina did that too, right?
Yes.
It was an amazing experience. We were able to board there, stay for the whole time, be able to work with a lot of people there in terms of extracurriculars. And also, like, we had a meeting plan. You saw the picture on Annenberg. It was an amazing dining hall. We had a great experience there. So that's one of the things that very memorable part of the whole 3 weeks.
Wonderful. And
That's us pointing to our fearless leader in the middle there. That
so
was
I saw a lot of the folks that we have, the team here that actually joining us online over Zoom, right? And I saw Yash in the picture, and I saw Arjun and right, and Tim and Chandrakant, and it was a wonderful 3 weeks, right?
it really was.
Yes.
So
It was fun.
Was it a lot of work? I mean, from academics perspective,
Well,
right?
Yeah.
as our professor, we should say it was a lot of work.
It was a packed session. But I think the on-campus experience is something that we are going to cherish all life, I think. People are going to agree with that. Yeah.
Excellent.
I
And
actually lived in Boston 25 years ago, briefly, and I took a financial accounting class because I had no idea what financial accounting was, and I was working for Liberty Mutual. And so my transcript actually is 2001, and then it goes to 2021. So I hadn't been here in 20 years. So it was actually great to come back and see both how much and how little the city had changed. And it was great visiting Harvard again, and
right,
really enjoyed it.
wonderful, excellent. Now I see that Dr. Mason Quick has joined us. Dr. Quick is one of the scientists and one of our sponsors. Dr. Quick, thank you for popping in and joining us.
Yes, hello.
You like to say a few words? Your work with the students here.
Yeah, I just wanted to take the opportunity to reiterate how good of a job the students did. It was a pleasure working with them over the last 6 months or so. Our project, I work at NASA Marshall Space Flight Center in the Earth Science branch, and we use high altitude aircraft instrumentation to look at lightning optical emission in thunderstorms. And we had a high definition camera on that instrument that we really previously just used for visual context to understand the measurements better. Well, we realized that this could be a source of a scientific measurement if we were able to use machine learning to extract cloud top measurements from that. So we worked with the data science team, and they did a really good job. Took a couple of tries with different approaches and techniques, and they were good at moving quickly and adapting these processes to extract the science data. So it was a really good demonstration and utility that they demonstrated. So it was a great project and good results.
Thank you so much. And as always, thank you so much for the support and the willingness and working with our students, and thanks again.
All right.
So what we want to do now is that perhaps that would be a good transition to maybe that we will let the team to tell us about their projects and what did they do and what kind of discovery and findings, right? And are you ready?
We're ready.
Yeah.
Okay.
Let's do it. So this is our team. All of us here, we have Dr. Lang and Dr. Peterson. Sorry, we didn't have a picture of him, but this is us. And we are doing our presentation on low frequency microwave reconstruction. Satellites are expensive. Meteorologists are racing to find cheaper, scalable ways of tracking evolving weather patterns. Ice clouds are one such weather phenomenon that is especially challenging to measure. Detecting them requires costly and specialized low-frequency microwave sensors. Yet, studying ice storms is critical, as they can be fatal, leave millions without power, and cost billions of dollars in damage. So, join us as we describe new ways in which satellite imaging, machine learning, and a bolt of lightning can come together to help predict the weather. So first, some background. Passive microwave sensing is a technique used to study clouds and precipitation. Different frequencies measure atmospheric phenomena at various altitudes. Lower frequencies, for example, have longer wavelengths and can penetrate deeper into the cloud, interacting with ice crystals without scattering or getting absorbed. This allows the radiation to reach satellites, where the intensity is measured in brightness temperatures, enabling scientists to detect and quantify the ice content within the clouds closer to Earth's surface. From 1997 to 2015, NASA operated its Tropical Rainfall Measuring Mission, or TRMM, which collected this low-frequency data. However, is now moving towards using smaller satellites, so the larger antennas that are required to read low frequencies will no longer be available. So how can we continue to measure ice storms in the absence of low-frequency microwave data? Well, our project's goal was to design a model that can reconstruct the 37 gigahertz low-frequency microwave data by using available high-frequency, infrared, and lightning data from TRMM. And I'll pass it over to Kasi to explain how we did that.
Hello, everyone. My name is Kasi Lakshmanan. I'm going to talk a little bit about the TRMM data. The Tropical Rainfall Measurement Mission was launched in 1997 and was designed to further understand rainfall in the tropical and subtropical regions. There are four main class of instruments that are part of the TRMM mission. The first one is the TRMM microwave imager. This is a 9-channel microwave radiometer that measures the intensity of microwave radiations emitted from the Earth's surface and the atmosphere at various frequency bands, typically 9, 19, 37, and 85 gigahertz. The second one is the precipitation radar. This is the first rain radar in space, which provides a 3-dimensional map of the rainfall. It measures time delay between the radar signals emitted towards the Earth and reflected back after encountering raindrops, and provides information on the cloud height. The third one is the visible and infrared system, an image spectrometer designed to complement the TMI and PR. The fourth and the final one is the lightning image sensor, LIS, which is measures the lightning flash rate differences among precipitation features. In this slide, we're going to talk about some of the most important features from the TRMM data. The figure to the left shows the probability of lightning by different brightness temperatures captured from the instruments in the previous slide. The lower the temperature, the higher the probability of lightning, indicative of icy conditions. In fact, the minimum brightness temperature at 37 gigahertz can be a good representation of the probability of lightning. The list to the right shows some of the top predictors that came up to be useful in predicting TMI 37 gigahertz. Before we delve a little bit deeper into the modeling process, let's talk a little bit about the data processing and the data engineering steps. For this, I am going to highlight two main aspects. The first one is the polarized correction temperatures. Polarized correction temperatures is an important concept in microwave radiometry for studying convection or rotation within the storm and precipitation. PCT reduces the contrast between land and water surfaces in microwave imagery, making it easier to identify intense convection and precipitation. PCTs are basically computed by linear combination of vertical and horizontal polarized brightness temperatures for frequency typically in the 10, 19, 37, 87 we talked about. The second aspect would be grid alignment. Satellite data can have irregular spatial coverage and coordinates. Standardizing them in grid maps these irregular coordinates to consistent spatial dimensions in the form of exact X dimension, Y dimension, and the different frequency bands. This makes sure that each pixel in the image is representative of a certain geographic region. Now, the data that's in the 3D images can be used to train deep learning models. We collaborated with the Georgia Tech Research Institute and NASA to process about 400 GB of TRMM data, which was spanned over a decade, and we created representative samples of data using resampling techniques. important defining characteristics of the TRMM data is the spatial smoothness with very little variation between adjacent pixels. So some of the traditional techniques that we could use, like data augmentation, did not really work for this type of data. Next, Tim Ginting will talk about the different modeling constructs and also talk a little bit about the swath data.
Thanks very much, Kasi. As we can see here, this is a visualization of the microwave brightness temperature progression. This was back during Hurricane Katrina back in 2005 from the microwave imager TMI. We can see the satellite take a rather sinusoidal orbital path here, and it's easily able to map the globe over this 4-day period. Just for reference, the areas in red actually indicate colder temperatures, while the areas in blue indicate warmer temperatures. And the visual information here is particularly useful for determining the characteristics of ice and water in the atmosphere. And this can be done by comparing emissions from different microwave frequencies. Just as an example, the 85 gigahertz microwaves are scattered by ice crystals in tropical cyclones, and this makes the cyclone rain bands appear colder than the surrounding areas. Just specifically here, Hurricane Katrina was in the Gulf of Mexico at the time of this visualization, and it shows up in the measurements as a greener, colder area in the middle of the warmer blue of the surrounding Gulf. As we can see here, each instrument takes different kinds of temperature measurements. Our main goal here is to reproduce the 37 gigahertz images, as NASA is moving away from larger, lower frequency satellites. And this is done by training deep learning models on images from other satellites and frequency channels, and using this data to recreate the 37 gigahertz images. We were very fortunate to have a solid foundation to work off of in the form of a baseline CNN model done by Dr. Michael Peterson from the Georgia Tech Research Institute. Our project involved building on this baseline model and then improving the contour and the intensity of the predicted images we see here to more closely resemble the original images. So given the time frame and the scope of the project, we decided to try a three-pronged approach and really hone in on models that best serve the project objectives. We use random forest models and linear regression models as they are computationally simple and explainable, allowing us to try many different iterations of the model. The CNN model is a great choice since it's designed to extract relationships between features from convolutional layers. Also, we wanted to have a model that would allow for direct one-to-one comparisons with the baseline model. And lastly, the UNet model has an encoder-decoder structure that captures features and reconstructs the original spatial resolution, which is critical when maintaining these relationship features is a big priority for us. And now I'd like to pass it over to Arjun to discuss the modeling process and the results.
Thank you, Tim. First, I'd like to direct everybody's attention to the graph on the left. Here we have a chart of model error. What that means is how good or bad our models are. The blue vertical bar is describing the baseline model that we were looking at earlier, and then the four models that Tim just described are the following color bars. Now, on the x-axis, we have this freezing in PR, full test set. Those are just temperature ranges. What really matters is on the y-axis, this RMSE, MAE, root mean squared error and mean absolute error. These are just different ways of measuring how good our models are. And the units are in degrees Kelvin. So what we can see here, just interpreting these charts, is we have these long blue bars. And that means that these models are less accurate. On average, they tend to deviate from what we expect by quite a few degrees of Celsius. But these newer models, the linear, the random forest, the neural networks, there can be 30, 40, 50% better, just much more accurate at capturing the true values, at allowing us to predict what we want to predict from the 37 gigahertz PCT. And then the chart on the right-hand side, this true versus predicted response. What this is describing is, all right, we have 85 gigahertz PCT. We're trying to predict this 37 gigahertz PCT. We know what the true values are. How well did our model do? Well, visually, if the orange predictions are sitting on top of the blue true values, then we know we have a pretty good, pretty accurate model. That's exactly what we're seeing here. Here's the convolutional neural network pixel predictions. We can see it pretty much sits right on top of those blue dots, which indicate to us that it's a pretty good model. And we have a lot of potential here. But it's not enough to just talk about numerical measurements and say, oh, this model is better than that model. Now we need to get back to brass tacks. We're taking images here. We're doing image analysis here. So let's take our predictions and put them back into images. The top chart there shows what the true 37 gigahertz PCT response looks like when converted into, of course, something that the human eye can comprehend, but into that gridded form that we can understand. And the following 4 boxes are the predictions from the individual models. And what we noticed is there's a little bit of a trade-off between contour, kind of like the shape that the images are making, versus the intensity of the pixels, like how green or how blue. And what we kind of came up with, or what we found across the board, is that the convolutional neural network seems to be the best of both worlds between the contour and the prediction. And that kind of makes sense because at the end of the day, this CNN, it is an advanced image analysis technique that's the same thing that's in your iPhones. It's the same things that are in the self-driving cars. It's just a very popular model right now because it's able to handle a variety of these more complicated image analysis tasks. That's not to say, though, based off of what we saw from the previous slide, that the other models are not very good as well. There are trade-offs between them in terms of explainability, power, cost, and those are things we want to consider as we move forward. So ultimately, just to recap, what are we doing here? We're trying to take a large, expensive antenna and reduce it. What does that do? Well, by reducing the complexity of the antenna, we're driving down cost. By reducing the size of the antenna, we're reducing its weight, which drives down cost. We have to be able to do these kind of satellite missions better, faster, cheaper. And if we can enable those kinds of things, then we'll be able to have more satellites and more effective satellite data collections. And that's exactly the kind of mission that NASA is trying to move towards. And what we believe is that with these models, whether it be the more traditional models like the linear model or the more complex models like the neural networks, there's just such a good range of capabilities. There's such a lot of potential between all of them based off of the use case that we can achieve those reduced costs and achieve those better outcomes and missions. And so for the next steps, what we want to do is take these models and evaluate them against the hundreds of gigabytes of data that's out there. We want to be able to see, can we predict things even better, even faster, even cheaper? And with that, I'd like to take a moment and thank my team, thank our amazing sponsors, and of course, our absolutely, and I can't say this enough, just fantastic, fantastic faculty. I'll pass it back to you guys.
Thank you.
All right, thank you.
So that's us, low frequency microwave reconstruction, and I'll pass it on to the second group to tell you about theirs.
Hi, everybody. So we're the Cloud to Cloud team. I'm Ian, this is Christina, and we will get started. So what we are working on is to basically be able to take cloud imagery that was taken from an overflying plane and turn it into height fields that actually describe the top of the cloud. And extreme weather events are rapidly rising. They're quite bad. The first Category 5 hurricane formed in June for the very first time. There have been Mumbai floods were in July last year, and there were also really bad floods in May in Brazil. And I personally, actually, while working on this, got to have some personal fun because a tornado hit my house in Wellington, Florida, which had not previously happened before. Generally, hurricanes cause tornadoes to form, but never before have we seen this many of them. 47 tornadoes formed, in which this was my neighbor's house. The same thing happened to my sister. this tornado was crossing Wellington. We have the swimming pool, and this is what it did in a matter of about 15 seconds. So this actually happened while working on predicting extreme weather events. And so why is cloud top height important? Well, it's, to put it bluntly, it's the very top of the cloud. It's the mean above sea level. The higher the cloud top, it signals that there are a lot of updrafts and convection, that is rising air that's very rapid. And these are closely linked to severe weather phenomena like thunderstorms, hail, tornadoes. Hurricanes are usually forecasted long before, but they are also extremely high. And you can see the height of your average plane there. And if we go, it also calibrates and validates radiometric instruments on satellites. And the instruments that we use are called the FEGS, which stands for the Fly's Eye GLM simulator. And it's called that because it literally looks like a fly's eye. And it's used to calibrate a satellite called GOES-16, which is a geostationary satellite. And so this thing uses multiple sensors, radiometers, cameras, and it's mounted on this thing called a NASA ER2 aerial laboratory, which is actually a slightly modified U-2 spy plane back from, you may have heard of that from a long time ago. And the crazy thing is, this is a modified picture. You can see how high this plane flies. It goes 70,000 feet, which is above 99% of the atmosphere and almost double what a normal commercial plane flies at. The FEGS does many things. As you can see, it has many radiometers. It also captures high definition images and other data. And it also has something called LiDAR on it, which is basically, it's very similar to radar. It's a laser that can detect the distance of something, but just a point. It can't do a whole range of things. It'll just be like the point the laser shines on. And we have a very catchy NASA video that explains all that with a really good soundtrack.
The Geostationary Lightning Mapper, or GLM, is an instrument on board GOES-16, the newest of NOAA's Earth-observing satellites. GLM detects the pulses of light produced by lightning and thunderstorms, and reports the brightness and geolocation of the lightning to Earth, where it is used to aid in severe weather forecasting. NASA has designed an airborne instrument to validate the GLM observations. The Fly's Eye GLM Simulator. Fly's Eye, or FEGS, is an array of radiometers optimized to measure the optical emission from lightning. It consists of 25 individual radiometers, each tilted at a different viewing angle so that they combine to create an image of the cloud top at a rate of 100,000 times per second. These radiometers are sensitive to a narrow spectral emission feature produced by atomic oxygen in the hot lightning channel. Fly's Eye also observes 5 additional spectral features, allowing scientists to investigate the physical properties of the lightning, and an HD camera to reveal details of the cloud tops. To view the thunderstorms from the top down, FEGS is carried on the NASA ER2 high-altitude laboratory. Fly's Eye will help determine the detection efficiency and sensitivity of GLM and advance our ability to understand and prepare for severe weather events.
And so here is what we got to see from the camera that was mounted on the ER2. As you can see, it's going through a small portal on the bottom, and you can also see it's a little bit warped. It's been going through a fisheye lens, which is why sort of there's a weird distortion where everything kind of looks a little bit oddly round. But this is what we had to deal with, and every 5 seconds, this LiDAR fires in the center of it, and it would tell us the height of a single dot in the very center of this photo. This is why it was a pretty big challenge. And one of the things we tried to do, the very first thing we tried to do, is try to use something called a monocular technique, which is where you just have a single image and you take it and you put it through a model and it tries to create what's called a depth map, which is something like what you see on the right. As you can see, just even a person looking, I mean, that thing looks like the moon. It doesn't really give you any details. It doesn't really help very much. And the thing on the right, that could be right. It could be wrong. It doesn't look like it's right. It looks like it's actually inverted. So again, to reiterate, these are some other pictures we have of the same from the same videos. We just had the height of the dot in the center. We didn't have like a full data. We didn't have a mesh that would sort of say, here is the image and here is all the different heights of it that you can train a model on. We just had what was in the middle. And so one of the things we've tried to do is we also noticed that you could use parallax. You could use this phenomenon where if you're in a car or if you're in a train in this case, things that are close to you move really fast and things that are really far from you move very slowly. So the mountains are barely moving, but everything in the foreground is moving faster and faster. So we can use that to basically, if we can track certain parts of the cloud, we can map it by seeing which parts move faster relative to the plane. And the first step that we had to do, we had to take this video and chop it up. We had to get the video. We had to extract the frames. We had to separate them into 1 second. We had to link them up with all of the LiDAR measurements. We had to also correct the fisheye. We had to basically undistort it. We had to crop it, and we had to correct it to make sure that after it was cropped, that everything was still in the right place. And finally, we did some data augmentation, which you can see in the last one there, where we tried to make things more clear. And this is, you can see this here. We use stuff like adjusting contrast and equalization using histograms in order to try and make things more visible. Now, these are pros and cons because the one on the left obviously is less defined. The one on the right has a lot of very clear edges. But if you're a person looking at this, it kind of looks like the one on the left is a lot flatter than the one on the right. So it became even more important to use motion to detect this stuff, because just as a person looking at these two images, the one on the right looks like it's got a lot more variety in it. So what we did is we created sequences of, this was the first, we used 2 methods. The first method that we tried using deep learning. So in this case, we took a sequence of 5 pictures. These are actually 1 second apart. And in the very last image, you can see a tiny little red dot, and that's where the LiDAR fired. Now, you notice that the LiDAR is in the corner. It's not in the center. Well, why is that? I thought it was in the center. That's because we also did this random cropping technique, because we didn't want these models to start knowing every single time that the dot was going to be in the center of the picture. So we wanted to take little random crops, move it around, make sure it was the right size, but that way the dot that it was actually being fed to the model moved around, and it wasn't always in the same place. What we did realize, though, is when we tried to train a model using only knowing 1 dot in the picture, is that it kind of did something terrible. It just predicted the dot. It didn't, even though we tried to make it predict the rest of the image, it wouldn't do it. And it would actually give us identical predictions for everything except for the dot in the center. So what we did is we split it up into two different types of models. We have one where we're just trying to predict the LiDAR. We are just trying to predict, using the rest of the map, this 1 dot in the center. And the way we did that, we use a CNN, which is a convolutional network. And that is designed to simply extract all the features and all the edges and all the marks. We then also combined that with the metadata. So we had stuff from the flight saying like the roll, the pitch, the airspeed, even everything down to its latitude and longitude and the time of day, in case any of that stuff mattered because of, say, the sun was setting and it would create different shadows. And then we fed that into an LSTM network. LSTM is, you probably heard of transformers these days. That's a much newer version, but LSTMs basically are allowed to model things over time. So it was able to take in these sequences of usually 5 images and work with it temporarily to make a prediction for the center. And we had decent results. The red line is what it was, what our predictions were. And they actually did follow. If you notice, it does, the movement of the line is very similar to the actual plane. And it's not nearly as different as it seems. This is the difference between there is about 200 feet out of 200 meters, sorry, out of 13 meters. And the reason for this is shown on the right. Almost all of the images we had were between 12 and 14,000 meters. So because of that, the model was just used to that. That was basically what it was seeing all the time. So this was an okay method. It would probably get better if we had more data. The next thing we tried was called RAFT, and this was to actually get like real mapping of the clouds. And so RAFT stands for Recurrent All Pairs Field Transforms, which is a great complicated word. And what it means is that it's using optical flow. It basically takes 2 images, it finds 2 pixels that it thinks matches, and it does that for every single pixel, and then it computes the movement of where is that pixel moving, and it creates a motion field, and then it goes back, and then it tries to see, well, now that we created a motion field, does it make sense? And then it goes, no, it doesn't. Well, let's adjust it, and it iterates, and it iterates, and it iterates, and it finally comes up with a motion field that it likes. And so we use that motion field. So we now have literally a map of where everything's moving to. And now we also know the height of the cloud, and we know where the plane is moving to, and we have the latitude and location. And we can actually use that and with the idea of parallax to calculate the heights of parts of the cloud. And then we also use the LiDAR to then adjust the whole thing. We can move it up and down. We can sort of train it with it. And in order to do this as well, we wanted to fine tune this model, because RAFT is a great model, but nobody is training this stuff on clouds. Nobody's doing anything with clouds, because honestly, you look at a cloud, even as a person, you look in the sky sometime, try and guess how high a cloud is. It's almost impossible because you can't even guess the scale. So one of the things we tried to do is we created custom loss components. Now, loss is a way to train these models, and you want it to be as low as possible. So the model tries to minimize these things. So one of the things we wanted to minimize was that we wanted to make sure that any movement, any motion that we detected could then predict the next stage. So you calculate the motion, and then you apply it to the image and check to see if it actually did move the way it was supposed to. And if it didn't, well, that's penalized against the training. Then we also do it with smoothness. We want to make sure that clouds are fairly smooth. Unless there's a gap between the clouds, there shouldn't be just like giant, triangular clouds, octagon clouds floating in the sky. So we try to make sure it's smooth. We also try to make it consistent. So we have flow consistency where we check the model and make sure that the clouds, we have the motion. We try to make sure that if the cloud goes forward and then the cloud goes back, it ends up in the same position it was supposed to in the first place. And then finally, we use the LiDAR to adjust it as well. We gave a slight loss. We had to be very cautious with all this stuff because anything too extreme really did dramatic things to the model. So here's an example of how this model works. Now, is this moving? It should be moving. It is not moving. All right. Anyhow, this is a, oh, it was moving. It was moving. So this is an example of a tower formation of a cloud. So this is a very, very tall storm cloud. So on the left, you see what it would look like through the porthole of the plane. And on the right, we have the cropped version because you have to feed them in as squares. So from that, here are some sequences. So we have at the very top, you've got 5 images ending with the LiDAR, which has been cropped in a random place. And then below that, the second line, those are all motion fields. Those are the motions calculated between each of the 2 pictures above it. So you have only 4 of them because there's 4 gaps. Finally, in the very last row, you'll see the one on the left is our fine-tuned one, and the one on the right is the original one. And you'll see on the bottom right, there are a lot of little dots there that are a little bit weird because those are caused by condensation on the lens, which we'll get to in a bit, but they were problematic. So finally, using that, we were able to create a 3D visualization of it. We were able to not only calculate it, and you can see the condensation marks there, but it was actually very cool. This was the first time we made some, at least for me, I was the one working on this, finally got some real results here. And then from that, we then had to stitch these together. So we took 10 of those images, and because they're each separated by 5 seconds, so this is 50 seconds worth, you can see the dots are in the middle there, and the plane was flying in a northeasterly direction at the time, so that's how it automatically mapped it this way. And because it's 50 seconds, the plane is flying at 200 meters per second, so this actually represents a 10-kilometer journey by the plane. And from that, we actually can generate a fully 3D visualization of the cloud path, including the giant tower on the left as it rotates. You see the higher green part is there, it's much higher altitude, and that was the storm cloud. And the rest of the team, so Christina is going to talk about the other methods that we used.
So taking a step back, we're thinking if we can track the points of the cloud and know their speed, then we can plug in with the other data that we have, which is the aircraft speed, and try to create some formulas to just calculate what the cloud heights are. So we're calling this the optical flow geometry driven approach. Basically, the main assumption we made is that the clouds are stationary. So thinking back to that train, the plane, we're just assuming that the clouds are stationary relative to the plane that's flying over the clouds. And the underlying idea, again, is to use the models to track the motions of the clouds with respect to the camera. So given that we already know aircraft speed and angles and such, so forth, as long as we can have models to get that speed, and then we can get our final point height result. So here we're using Lucas Canade to track points within a cloud and see how they're moving. So on the left-hand side, we have the original frame. So here's just the fisheye lens, and you can see that on the edges of the fisheye that some of these paths are curved. This is due to the fisheye effect. So for a sanity check, here we're actually trying to flatten out that image, and you can see that the paths towards the edge of the camera now, or the viewport now, are now straightened out. So to start with, we have that center point height. So we're trying to see, can we actually get close to predicting that LiDAR height? So we're tracking points in the center, that 48 by 48 pixel center. And here we just have the coordinates of a couple pixels. So blue is actually corresponding to a blue track, purple and green. So these are just 3 points I took out from some of the points we're tracking there. So given that tracking, we know their X velocity, their Y velocity, and plugging into the formulas, we're not going to go into that here. We were actually able to output predicted heights. And when we averaged those heights together, we got 13,320 meters, and the actual LiDAR height was 13,131 meters. So we were very, very close. So next, we want to actually try to generate the full cloud tops. So here we're using TVL1 to do the full frame tracking. So you can kind of see these are vectors that are being tracked, motion vectors, and then for some of these, there's not really much motion going on. And again, those are back to what Ian was talking about with some of these points, some of the condensation on the lens, trying to kind of hindering a bit of the tracking there. But what we ended up with is we're actually able to create a full 3D height field. So on the leftmost side, we can see the cropped image. And then here's just a top view of the heights that we came up with. And you can actually see that we have that same patch of sky here, and we're actually picking up all the clouds. And then here in the, we can actually see that all of the predicted heights for the cloud is within the expected range between 13,000 meters. And so with that, on the left-hand side, we started stitching together 1 minute's worth of height fields. And then in the middle, if you're in the plane, like if you imagine you're in a plane looking straight down, this is like a center slice going over 140 kilometers of the flight. And then on the rightmost hand side, where if you imagine you're in the aircraft looking at an angle from the side, this is like a side slice, also going over a portion of the flight. So I'll hand it back to you, Ian.
We're just about done. And just in conclusion, the research that we did here, I believe it's fairly novel in the sense that not much has been done with computer vision and cloud height simply because it is incredibly difficult to do. Clouds are very, very sparse in features, and it's very difficult to track things. Hopefully this will help NASA in a way to be able to then use this information cheaper without as many instruments to then both calibrate instruments as well as get the cloud top heights. And just some future work, our CNN LiDAR predictor, obviously it was a little bit off, and I think we could try some future transformations. And then secondly, the lens condensation was just, honestly, it was my nemesis throughout a lot of this. And the reason for it is that when you get, imagine you're in a car and you're driving by and you get some snow on the window. The snow doesn't appear to be moving. So it seems like it could be infinitely far away, just like the mountains. So for the computer vision algorithm, if something's not moving, it's very, very far away. So it appears as holes in the clouds. So literally you get all these punctures in the clouds, and it's very difficult to remove them because in order to like impute or just generate your own replacement, you'd have to know what was there and you'd be inventing your own information. So we're still experimenting with different things for that. And thanks for joining us. As you can see, as I mentioned, it was difficult, and even the newspaper picked up an article about me here when I lost it one of the nights. And we'd like to thank our great professors, Dr. Wong and Dr. Elston, as well as our sponsors at NASA, Dr. Lang and Dr. Quick. And that's it. Thank you very much.
Excellent. That was a great presentations, and it was amazing work, right? And what we're going to do now is maybe that we open up the forum. If anyone has any questions, if you those of you joining us online, you can type the questions, and that we will try to respond to some of those questions here. And now we have a couple members of this team here, Yash and Chanchok Kant. And so y'all want to say a few words here?
Hi, Bruce. Hi, everyone. It was incredible to work with my teammates, have your guidance as faculty, and with the NASA scientists to work on this project, especially coming from a background knowing nothing about clouds or satellites and aircrafts. It was really a steep curve at the beginning to learn about them. And I think especially during the pre-Capstone residency, we spent a lot of time reading about the literature around this. And then going around in the last 6 months, actually doing the project, it was an incredible experience. Often frustrating, like Ian mentioned, you are waiting to get a breakthrough for a really long time, and you have to have the patience to get those results.
Hello. Hi, Bruce. Hi everyone. Actually, this was an incredible experience last 6 months working on this project. And I'm really missing our Sunday meetings. So every Sunday we were doing meetings, and the work really everybody put in this was really incredible, and we are getting also good results. So thanks everybody.
Excellent, excellent. Find to be as the biggest challenge when you start working on your capstone, and how did you overcome it? Well, that's Ramila. So Ramila is actually one of our current students, and that if Ramila, if you like to join us and that have a conversation here, that maybe that we can get Ramila online here. Okay, all right. So well, anyone wants to start answering the questions?
Yeah, sure. I would say that the biggest challenge was that it was a completely new domain. I didn't really know that much about cloud tops. I didn't know why it was important. I had a feeling when we took on the project it was going to be difficult. I didn't know how difficult it was going to be. And frankly, the first approach that I had, which was, as I mentioned, I thought that I could, just using a single point, but using thousands of images, I thought I could get it to start predicting the entire image. And no, I couldn't. It was not going to happen. And I had to find other ways to do it, a lot of experimentation, a lot of reading. And yeah, the amount of things that I tried that didn't work was what made it especially challenging. And it's hard because, especially when things don't work, it's hard not to get demotivated. But then you never know when you try something and suddenly there is a perfectly good result on your screen. So it's definitely worth to keep trying. That's what I would say. I mean, we knew that even if we failed miserably and we weren't going to get anything, we'd still be able to like document all the things that didn't work. So that wasn't really a huge concern, but I didn't want to go down that route if I could help it.
I'll also say one way that we would overcome those types of challenges is getting on calls with our sponsors, which was really helpful. It would get us unstuck quite a few times because, like Ian said, we just didn't really know this domain that well, and they did, and they were really, really nice about guiding us in the right direction.
One thing I would say is for our project, I think the volume of data was a big challenge. We had about 400 GB of data. TRMM missions are it's a 10-year running mission. So it was back to the basics. How can you create representative samples from data that's that far beyond, and in terms of volume? And the second thing was in terms of the events, most of the time you would find only clear sky. So those are not indicative of convection or precipitation. So we'll have to do the right sampling and create the right data to be able to build the model. So I think two of those are the two issues that we faced. I mean, among many others, but those are the things that come to our mind.
Thank you very much. And that we have a question from Sanan, and Sanan is saying that can you identify a specific class you have taken that play a significant role in the success of this project? A particular class?
Yeah, I can, sure.
Yeah, many, I think computer vision, I mean, so again, it goes back to basics in terms of machine learning, deep learning, understanding of statistics, and going back to creating representative data sampling. I think specific courses in the sense that we had deep learning classes, advanced deep learning, which was very helpful, and computer vision classes.
Yeah, computer vision was very helpful because we did use a lot of computer vision techniques, especially understanding how CNNs work and whatnot. I also took a class that is not available anymore. It was deep learning for NLP and machine learning training, so that was also very helpful. And I think there are similar components. I didn't take them, but the 109 and A and B, I think 109B does a lot of the similar stuff that I would have done in the NLP class. So if you can take 109B to, at least for that specific thing, learning this type of deep learning and PyTorch, and it can be very helpful.
I think from my side, a lot of the I didn't actually specifically take a computer vision class, but the 109B, just like knowing how some of that worked was very helpful. But I do wish I took more computer vision, and Dr. Elston actually helped us a lot of kind of giving Chandrakant and I like a crash course in what he would typically teach in his class. So that's how we got the Lucas Canade, the TVL1, to do some of those approaches and to customize it for the formulas that Chandrakant came up with to try to like extract the X velocity, plug it in, and then compute issues too, like trying to speed up that runtime. Was spending a lot of late nights on that. But I want to thank Dr. Elson again and Chandrakant for working. We're also all working together to get our knowledge up to speed on that.
Excellent. Let's see. We have one that's asking, what was the source of largest data noise in the data during the data engineering process?
Our data was problematic because we had to drop out anytime the airplane was turning. Rely on the fact that the two data sets were separate. The actual flight videos and the data set showing all of the metadata, they were two separate data sets, and we had to sync them. Actually, Yash did all of this, so good work, Yash. And in order to do that, there was a lot of, not everything got filtered out. Sometimes the airplane would wobble or move. And when it did that, at least for the deep learning model, I'll get her in a second, but when I did that, suddenly it would generate this smooth cloud going up to 50,000 meters in the sky. Like, I don't think there's a 50-kilometer cloud out there.
Yeah, for our approach, like Chandrakant and I were like, what are these outliers? And I manually looked at it and played the video, and I was like, oh, there's turbulence. There's like the camera is wobbling or realigning. So our sponsors did help us like to identify a lot of data points that we could drop. But I think we could do well to go back and try to figure out what those other outlier points were.
If I can add, Christina, I think fisheye correction was also one of the noise in terms of, especially for the optical flow geometry approach. So again, I think the help from our sponsors to get the distortion coefficients and then the correction that we did was, I think, one other key aspect of data cleaning that we had to do.
And from our perspective, I would say a lot of the things that we thought were noise were actually how we had to do the data engineering piece. We had instances where we had to apply some techniques to be able to reduce the data because they were actually sensor errors. Things like that, because these are missions that were run long time ago and data still exists there, but they were not actually useful for us. So some of the things that we thought were noise were actually sensor errors that were happening in the data collection. So we had to go back to like the traditional data exploration techniques to be able to do it one by one. And so for some, and a lot of cases, the volume of data was large as well. So those are some of the things that come to my mind.
Excellent. And I guess we have some questions here regarding the study, right? And it says that any advice for someone starting out in the program, juggling a full-time work and family?
I would say do it. Just do it. I also was concerned about that when I first started, but I think it was one of the greatest experiences I did. And now I've got a master's degree and I'm really proud of it. And I think it's going to open up a world of opportunities, and you just get to meet so many different people that you would never expect. I think it's worth the investment in time, money, whatever it is. I would say do it.
I would say when I started, I had a 6-month-old daughter and I'm married. And I would say that you need to have your spouse very much on board if you have a spouse and if you have children. Oh my God, because you will need their help. They are absolutely crucial because it is obviously hard to raise kids. And if you've got kids and you're also working full time, which was my situation, I owe her a lot. So shout out to Maria, my wife.
What I would say is pick your courses wisely. I think, start for learning for the sake of learning, not for the sake of the degree. I think that's an important aspect. I picked some of the courses that were very helpful in trying to come up with a repertoire of courses that you would come out with, which are very helpful. In terms of the cutting edge, right? So I think that's one thing I would say. Sometimes it will be overwhelming, in terms of some of the classes are very advanced and cutting edge. So I think, I think you should pick some of those and keep moving. Keep moving. That's important.
I would say it's okay to take breaks too, though. I stretched mine out over 5 years. I did take breaks certain semesters for like just planning for family events or just like job transitions. But yeah, just do it. Definitely worth it.
I heard there was this crazy guy who did it in 2.5 years.
Yeah.
Yeah. Brendon, any advice for people new in the program?
Enjoy the ride. It is long. And like I said, I had tremendous support along the way. Because you need that. There's certain times you get stuck in a class and you're like, oh, why am I doing this? Never lose focus of the goal. Never lose focus why you're in the program and what you want to do with your master's degree. And I think when times get tough, just focus on that at that end point, and that will get you through.
Thank you. All right. So I guess someone mentioned up there, right? And so where will you be in July?
Oh, all right. You guys, okay. So
where will you be?
all right, you're going to be in Geneva.
Yes, all of us.
All of us.
Yeah, we're doing the UN conference AI for Good in Geneva, Switzerland, and we'll be representing Harvard and explaining our projects together.
Wonderful. And so yeah, so this is amazing, right? And last year that we had our Capstone team actually went and to the AI for Good Summit in the United Nations, and they were basically representing us, and they're taking our Capstone to the world stage. And once again, and these teams are now invited to Geneva. And this year, the Geneva Summit is going to be in July, and they will be there. And as our proud alum, this graduation is in May, right?
That's
so
right.
That's
they
right.
will be our proud alum and representing us, and this is wonderful. And thank you everyone, and for your effort and your work in this amazing Capstone project, right? And that you made us proud. And so everyone, this is basically concluding the event and our program for tonight. Have a wonderful, wonderful evening.